Hello, today we are going to discuss work sharing and synchronizing primitives which are done by the operating system in conjunction with the hardware on which the OS is running. So, this is the agenda for the module. We will begin with an introduction, then we will see the data races and synchronization, then we will have a look at how critical sections are implemented using locks, then we will look at two other concepts, that is atomics and barriers, and we will end up with a summary. So, let us begin with the introduction. So, as you all know, sequential programs, they involve execution of instructions in an order, one instruction after another, which is decided by the programmer. A simple C program is an example of this. However, supercomputers use parallel programming techniques in order to achieve better performance. So, these parallel programs are bound to make use of multiple CPU cores, wherein each core is performing a task independently. Though these tasks are performed independently on the CPU cores, at times they need to interact with each other depending upon the algorithm that is being implemented by the programmer. This results in concurrency. So, concurrency means that multiple tasks of a program are run on a single CPU core. Now, how does this happen? That happens because the CPU core uses time slicing to switch this task in quick succession such that one thread, as the task is called, is run at a time. And these tasks or these threads as a result are interleaved over a period of time, because essentially a CPU core can execute only one thread at a time. In cases of systems which have CPUs with multiple cores, these threads need not run on a single core, but they can run on multiple cores and they will run in parallel, because the OS can assign a thread to a core. So, let us look at how this works in two cases. In first case, we have a interleaving, that is multiprogramming, which is on a single processor. So, here you will notice that process 1, when it ends, its slice ends, process 2 starts. When process 2 ends, the CPU executes process 1 again, and when process 1 finishes, the CPU core is assigned to process 3, and then process 2 and process 1, like this it goes on. Sorry, it should have been from here, when the process 2 ends, the process 3 starts. In this way, what you see is that the interleaving happens on one processor such that only one process is running at a time. However, if you look at a system which has got multiple processors, in which case you see that while process 1 is running, at the same time process 2 is also running. But when process 2 ends, the same core is assigned to process 3, and when it ends, the core again comes back to process 2. However, in between there are overlaps, that other processor core is being used by multiple threads. So, this happens when you have multiple cores and multiple processes running. So, thus we see that not only interleaving takes place in this case, but overlapping also takes place on the CPU. Taking this forward, let us see what are the issues that can happen when such a system is implemented. The first thing to look at is data races and how it is mitigated using synchronization. So, let us first look at what a data race is. A race condition occurs when two threads are running and they try to access the same variable at the same time. So, obviously these two threads are running concurrently on two different cores and they wish to access a common variable. The issue is that this is likely to cause problems sometimes. Now, let us see how this is going to happen. Because race condition exists, the program that is having multiple tasks can result in an error. This error could be of two types. One is indeterminate. Indeterminate means you cannot be sure as to what the result is going to be. I will explain this with an example later. Another issue that can happen is inconsistency. Inconsistency means that you run the same program multiple times. It is not ensured that every time you will get the same result. You may get different results. This will be clear to you as we go ahead. The reason why this happens is because there are two threads are running on two cores, and the order in which these threads are running on the core decides what the result is going to be. Essentially, the output that finally we get when the program terminates, when all its threads terminate, is decided by which of the two threads in this case finishes last. Now, it is difficult to determine which thread would finish last because the OS is going to schedule this task dynamically depending upon the conditions at that time, and as mentioned earlier, it is indeterminate to know beforehand which thread is going to finish last. So, let us take an example. Now, we have two threads and both these threads are accessing a global variable called x. What the threads are doing is they are reading the variable and incrementing the variable. Now, let us look at two situations. In the first situation here, as you see, thread 1, the integer value that of x is initially 0. When thread 1 reads that value, it gets it as 0. It increments the value and it using 0 as the value, it increments it, it becomes 1, and when it writes back, it writes 1. Now, in this case, thread 2 is scheduled after this operation is over. So, when it reads the value, it reads it at 1, the value that it increments is 1, when it writes back it is 2. So, what we have seen here is that there are two threads, each thread is incrementing the value of a shared global variable x. Both the threads are able to run one after another in this case. As a result, the value that you get is correct. Okay, now let us look at the second case. In this case, again there are two threads, both the threads are reading the value, increment the value and writing it back, but the way the threads are scheduled makes the difference. So, in this case, first thread 1 reads the value, which reads it as 0, then thread 2 reads the value, which it again reads as 0, thread 1 increments the value from 0, thread 2 increments the value from 0. Now, thread 1 writes it back because it has read 0, it is going to write it as 1. Now, thread 2 writes it back, which it has read as 0, it is again going to write 1. That means, the value written by thread 1 gets overwritten with the same value that is written by thread 2. So, here the result is 1, which is incorrect. The result should have been 2, which happens in case the two threads are scheduled in such a way that this process of read, modify, write happens one after another, like here it for thread 1 does it, then thread 2 does it, whereas here these steps get interleaved. As a result, you get a wrong value. So, this is a race condition wherein wrong results are obtained because of the way the threads are scheduled. Now, let us see how we can mitigate it. For that, there is another example that we can see in a real life. Let us say there are two persons who want to use a restroom and they enter it by opening the door of the bathroom. So, we have to ensure that when one person is inside, other person does not get access to that bathroom, and that is a very simple trick that we use, that is we use what is called as lock and key. That is, when the person enters the bathroom, he locks the room. As a result, the second person does not have access to it because the room is locked. So, that is precisely the thing that we do here. We have again here thread 1 and thread 2. They are performing the same thing. First they are reading, thread 1 is reading, then it is incrementing the shared variable. Now, let us see how synchronization can help in dealing with races. Let us take the example of bathroom that we saw in the previous slide. How does one guarantee that only one person has access to that bathroom at a time? We use the method of lock and key. So, same thing we can see here. There is thread 1 which is let us see how synchronization can help us to deal with the problem that we faced with races in the slides earlier. We had used the example of bathroom as a mechanism to illustrate this. So, how does one do it in practice? We use lock and key. The person who enters the room first locks the door. As a result, only when he comes out, the second person is able to do it. Same example is shown here. We have thread 1 and thread 2. Both of them want to use the shared variable x. What are the steps that we do? The steps that we do includes, first thread 1 gets an access to the shared variable. In the previous example, shared 2 also wanted to access the variable, so that is step number 2. However, it is unable to get access to that variable because we have implemented wait. Share variable x gets incremented by thread 1 and then it writes. So, that is step 3, that is access is completed. When this access is completed, then thread 2 gets the access in the fourth step. Now, it increments the shared variable and then it proceeds. So, now here the variable value becomes 1, here it reads as 1, makes it 2 and the result is correct. Hence, what we see is that by implementing such a synchronizing mechanism wherein exclusive access is granted to one thread at a time followed by next thread, we are ensuring that the race condition that existed in the example given in the earlier slide is prevented. However, when you do this, there are certain overheads, because we just now saw that thread 2 has to wait. As a result, it affects the performance. So, when you implement such a mechanism, there is a chance that the overall performance may slightly suffer, but the results are always consistent and the results are always correct. Now, how do you minimize this? The only way is to minimize the amount of synchronization that is implemented in your program, and that can be done only by the programmer by restructuring the code, which may also need restructuring the algorithm that is being implemented. So, how do we reduce these overheads of synchronization? Here is an example. Here is a processor that has got two CPUs, CPU 1 and CPU 2. Each one of these CPUs has got two cores, core 1 and core 2. Each core has a private cache and each core has a public cache. Now, the variable that is implemented is in shared cache. The variable x has to be in shared cache. This figure in this case shows that whenever the private cache is updated, the public cache is also updated. Same is the case here. Thread 2, when it updates the private cache, it also updates the public cache, and you can see that there are multiple writes that are happening between L1 and L2 caches. Here the overheads are more, but takes the second example in CPU 2, wherein the algorithm is same. However, we are ensuring that only when necessary the L2 cache is updated. As a result, this results in a better optimization and the overheads are less. So, the L1 cache holds a private copy, whereas L2 cache holds the public copy. The public copy is shared between the two threads, and in the second case here, as you see, the time it takes to update the shared cache is less, because only when necessary the variable x in the shared cache is updated. Now we look at another methodology called as critical section, which is handled using locks. Again we have the same example here, that is we have thread 1 and thread 2, and both are accessing the same shared variable x. Now there are two types of threads, one which is called as contention only threads, wherein the threads share the cache but they do not share the data. That means the code is running in the cache, however the data that is in the cache, the private cache particularly, is not shared among the two threads. This is a situation where there are no issues. However, when you have the data sharing threads, at that time we have to take care of, through some mechanism, the problem that was described earlier. So, as mentioned in the previous slide, the shared variable x is going to be in the L2 cache. So, it is not a private cache, but it is a public cache. So, let us see how this is handled. So, these are the steps that are followed, that you would have realized in the previous slide, that the first step is a read operation that happens here, read operation. Then you perform some operation on the variable, like in the example previously that we saw, we were incrementing it, and then you write the variable. So, this is being performed by two threads, thread 1 and thread 2. So, if there is a read, modify, write operation, then we have an issue. Sometimes there are situations where the threads may only read the data. If they are just reading the data and not modifying it, then any number of threads can do it in any order and we are not going to face any issue. The issue comes when you have a situation when there is a read, modify and write. So, this is implemented using another method which is called as critical section. So, let us see how critical section works. So, how do we perform these three operations, read, modify, write? Here is one way of doing it, by implementing it in a code itself. So, that code which does this read, modify, write is called as critical section or CS. Why is it called critical? The reason being that while that section of code is being executed, it should not be interrupted by any other thread. That is the basic idea. So, the way it is implemented is that a code enters the critical section, which will consist of multiple instructions. It will do its job of, like in the previous case, incrementing the variable x, and then it will exit. Once it exits, then only another thread should be able to use it. It will also have its critical section. So, if this is where the time is increasing, then first thread 1 gets an exclusive access to the variable x. It does the operation that it wishes to perform, like increment, and at this point here it exits the critical section. When it exits the critical section, that time is ripe for another thread to enter its own critical section. So, for this duration, no other thread will be able to access the variable x. Now, the mechanism to ensure this methodology that I described can be done using lock. So, essentially we are trying to give a guarantee that no other thread can interrupt the thread which is running by implementing this lock mechanism. What is the result? The result is that the thread which is accessing the variable gets exclusive access, and mind you that the access is to a shared resource which another thread may be wanting to access. Now, what is this shared resource? Typically it could be a memory location, then it could also be a peripheral device like a hard disk or an another IO device, or it could be a network connection on which a packet is being sent, or not just memory location but a collection of memory location which forms a data structure. So, the logic that is used is as follows. The first step is, at the beginning of the critical section, the thread acquires a lock. Once it acquires the lock ensures that it can now access the shared resource without being interrupted. Once its job is done, it will release the lock, and now you proceed with the code after critical section, where any other thread gets the right to access that variable. It will also implement a critical section in it because it does not want the first thread or any other thread to interrupt it. Now, what is this lock? One of the examples of a lock is called as mutex. Mutex stands for mutual exclusion, and this mutex lock uses the feature of lock and unlock to protect the critical section. In this example, prethed.h is the header file which helps us in creating the threads. Count mutex is the mutex that we are trying to understand, and count is a variable which is shared. Now, here is a module, a section of code which will increment the count. So, what does it do? It will first acquire the lock by calling this count mutex as a variable passed on to locking the mutex. Then it will increment the count, then it will release the lock by calling unlock. So, these primitives help the section, this is the critical section which is protected on one side by the lock and other side by the unlock primitive. This is how mutex work. Internally, if you wish to understand how mutex is implemented, then every mutex is a binary variable which can take a value 0 or 1. The mutex is initialized to 1, which means a thread can gain access to this mutex and enter the critical section. The moment it enters the critical section, it decrements this value to 0, which means it has acquired the lock. Now any other thread which is trying to gain access to the mutex will see the value to be 0. Because it is 0, it will not be able to acquire it. Subsequently, the thread that acquired the lock is going to finish its critical section and it is going to make again the value 1. Once it becomes 1, then it is available to any other thread to gain it. Thus, at a time only one thread gains the lock, acquires the lock, uses the variable and then unlocks it so that any other thread can use it subsequently. Now there are certain primitives like atomics which aid in doing this. So let us understand what it is. So essentially atomics is an instruction that can execute without interruption. So this is the same thing that we saw for the critical section, that we do not want the critical section to be implemented, and atomics is one way of doing it. Here there are two examples, one is called as test and set, other is called as compare and swap. So let us see how this works. So here we have this function called test and set, which returns a boolean value, that is true or false, and it operates on a variable called target, which is in a memory location, and the pointer to that is called as a target. So what is that we do? We first use this return value as a local variable which reads the current value of target, and that is returned. However, before returning we set the value to be true, because as the name suggests, we have to not only test what the value is, and we have to set the value before we exit the function. So now there are two possibilities. Let us say the value of that target was false, so that is returned as false, and if it was true, then it is returned as true. So the original value of target is returned by this function. Now how does we use it? Let us look at this second piece of code which implements the mutual exclusion using test and set. So the first thing that we do is we have a variable called lock which we pass to this test and set, and while this, when you call this function and when it returns true, you will proceed. If it returns false, you are going to wait here. The moment that it is false, that means somebody else is using it. Once, so it will keep waiting till it becomes true. When it becomes true, you will go to this critical section, perform it, and now you make it false, because now you have finished the critical section. So what have we done here? We have implemented a mutex by using an atomic instruction called test and set. Another example is compare and swap. So in this case what happens is that if you look at this function, then it retains, compare and swap returns an integer value, whereas it expects a value which is originally present, which is to be compared by an expected value passed by the calling function, and it returns a new value. So let us see how it works. You define a temporary variable which copies the value that has been passed to it by the calling function, and if the value that is passed is same as the expected value, then because the function is comparing, and if found to be comparison, if it is true, then we assign the new value that has been passed by the calling routine, and the value that was originally there which we had copied in temp is returned. So again here is an example where you use for using the same concept as before, where we have lock as the variable that we pass, and we say that if the value of the lock, if it is expected to be 0, then replace it by 1 and return it to me. So, in this case what happens is you call it, and if it returns as 1, then it proceeds, you perform the critical section is over, make the log 0 and then the code proceeds. So, these are the two ways of implementing mutex. One, as we saw here, was the test and set, and the next one is compare and swap. Atomic operations are typically performed on a memory location, that is an address, as we saw in the examples before. Now, there is a cooperation that is needed from hardware to ensure that no other thread can access the memory location until the atomic operation is complete. As a result, any other thread which wants to use it is held in a queue, in a waiting queue, and as a result all threads can perform the atomic operation in a serial manner, and which ensures that the things are done in a proper manner. Now, let us look at how barriers are implemented. Now, what is a barrier? Let us look at examples of barrier in real life. Here is an example wherein you must have seen railway crossings, wherein the road traffic is made to wait till the train passes. How is that done? This is the level crossing where there is a barrier. This barrier is lowered. When the barrier is lowered, the road traffic cannot cross the railway line which is here. So, all vehicles have to wait if the barrier is down. Now, the concept here is each of these vehicle would have arrived at a different time, and you can see that they are in a queue. So, obviously this bus has arrived later than the car, and the car has arrived later than this jeep. However, when the barrier gets lifted, all vehicles can proceed together. So, as a result, the concept of barrier is it makes the threads wait till certain event occurs. So, here is the application of that real life barrier to threads. All threads, they have to wait till they reach a certain points, and this now let us see how barriers are implemented for threads. The concept is that while all the threads are running, some threads are going to finish first, some threads are going to finish later, just as in case of vehicles arriving at different points in time at the level crossing. The program that is having these threads is divided into phases, and the phases are separated by barrier, and all the threads which are running in a phase, they have to reach the barrier and they have to wait. They cannot cross the barrier until the barrier is released. As a result, the programs or the tasks which are running before the barrier and the tasks which are running after the barrier, they cannot be concurrent. Only when those tasks which are before the barrier, all of them complete, only then the tasks that are after the barrier can proceed. Now, how is this useful? There are situations where there are dependencies of one task on the other. So, you have to ensure that the task which is dependent has to wait till the other task finishes, so that the results produced by the other task can be used by the dependent task. Sometimes consistency and coherency has to be maintained across the shared data, that can also be implemented through barriers. There is a feature called as checkpointing in running parallel programs, wherein the state of the program is saved and then it proceeds. How is it useful? In case one of the hardware goes bad, then you do not have to restart the program, but you can restart from the point of the last checkpointing. This helps in saving time in terms of rolling back to the starting point rather than starting from the point where the last checkpointing is done. Essentially, barrier is a synchronizing mechanism. Let us now summarize what we learnt in this module. Concurrency was the starting point. We said that parallel programming needs concurrency. While concurrency is helpful in improving the performance, it introduces certain side effects. These side effects can introduce errors which leads to incorrect results. However, the golden rule is that in quest for reaching higher performance, we can never sacrifice accuracy. In order to make sure that accuracy is maintained, the side effects have to be mitigated at every step. Synchronization methodologies is one of the ways by which we can overcome race condition, which is one of the side effects. Another way of doing it is implementing critical conditions, and for that locks come handy. To implement locks with help of the hardware and the operating system, atomics are implemented, and atomics lead to mutual exclusion. Another concept which helps in maintaining the overall flow of the program is through barrier. They help in keeping various threads synchronous. Now, these are the primitives that are offered by the processor, the hardware system, the drivers and the system software that work in conjunction. These basic concepts are further used by frameworks like OpenMP, MPI and CUDA, which give further functions to the programmer in order to write programs which gives correct results and consistent results. Thank you.